In a universe built mostly from silence and hydrogen, there is a rumor of impossible wealth. A world that glitters not in metaphor but in metallurgy. A sphere forged entirely of gold, reflecting its star like a celestial coin. A signal arrives in the night, dips in starlight too deep for a world so small, a mass too heavy for the radius given, a whisper of density that should not be. In empty control rooms and glowing labs, monitors breathe their cool light across patient faces. If the numbers hold, then somewhere in the darkness, a planet moves that could outshine every treasury ever imagined, where mountains are malleable, rivers never rust, and sunrise pours across a surface that conducts heat like a thought. Such a thing would change the story of matter. It would challenge how worlds assemble, how elements are mixed and sorted by gravity and time. It would speak of violence in the galaxies and a chemistry running backward. It is a fable, and yet every fable begins with a question. Could the cosmos mint a planet of pure gold? The shock is not aesthetic, it is arithmetic. Gold is not a common word in the periodic language of the stars. In the sun, it is a trace upon a trace. Across a protoplanetary disk, dust, rock, ice, and metals swirling in a newborn system, gold exists in parts per billion by mass, seeded by rare cosmic catastrophes. In planetary chemistry, it is fiercely siderophile, a lover of metal that flees the mantle and sinks into iron, hiding in cores. It does not stay near the surface. It does not congregate. It does not rule. That is why the headline feels like a fracture. A planet made of gold appears to violate the cosmos's bookkeeping. Even if every atom of gold in a typical disk could be gathered together, the horde would not approach the mass of a small moon, let alone a planet. The numbers do not fit. And yet, for a tense day or two, the numbers on a screen sometimes seem to. Exoplanet catalogs are built from two measurements: the radius from transits, how much a planet dims its star as it passes, and the mass from gravitational tugs measured by radial velocity. From these, density is inferred. A handful of worlds have come back with densities that strain belief, values nudging or exceeding what pure iron would allow. Papers are careful, headlines are not. World of metal, they say. Planet of gold, they wink. But physics is not a wink. There are lines on the mass radius diagram, drawn by researchers like Sarah Seeger, Li Zeng, and others, that map what is possible. Silicate worlds trace one ribbon. Iron worlds trace a heavier one. Above even that, there is no room for a pure gold world to sit. The shock is simple. A golden planet would not merely be rare, it would be a contradiction of abundance, of condensation chemistry, and of planetary differentiation itself. The rumor becomes a mirror, and the mirror reveals what is actually being seen. NASA's planet-finding machinery begins with light. Kepler taught how to feel the tiny heartbeat of a star when a planet crosses its face. TESS now tiles nearly the entire sky, catching ultra-short period worlds that sprint so close to their stars that their years last hours. Ground-based spectrographs, HARPS N, Carmines, Espresso, listen for the star's wobble, the sign of mass. Gaia refines the distances and true sizes of stars, correcting planet radii in turn. On this chessboard of data, a pattern emerges. Some rocky exoplanets cluster into an unexpected category, super-Mercuries. GJ367b, discovered by TESS, is smaller than Earth but nearly as dense as pure iron, implying a world with a huge metal core and only a thin silicate shell. K2229b tells the same tale. Kepler 107c appears to have a density far higher than its neighbor, as if a giant impact stripped away its mantle. None of these require gold. All of them hint at violence, heat, and loss. Those lines on the mass radius plots, their curves shaped by equations of state measured in diamond anvil cells and shock labs, show that density alone is not destiny. Many compositions can fit the same point. A planet could be iron-rich because it formed in the inner disk where metal condensed before rock, because its silicate mantle was blasted away in a collision, or because stellar X-rays and extreme ultraviolet light boiled off lighter materials, leaving behind a core. When NASA's Psyche mission launched in 2023, headed for the metal-rich asteroid 16 Psyche, the headlines returned as jokes. A rock worth more than all economies combined. But Psyche's real value is not currency. Radar returns and bulk density estimates suggest a fractured, possibly porous body. Metal, yes, but mixed, complex, strange. Psyche's instruments, a gamma ray and neutron spectrometer to map elemental composition, a magnetometer to detect the fossil memory of a core, imagers to read its surface, will constrain how metal worlds piece themselves together. It is not a planet, but it is a clue. Meanwhile, far beyond the sun's influence, a different instrument listens: the LIGO and Virgo interferometers. In August 2017, they heard two neutron stars merge. Telescopes across Earth and in orbit, Hubble among them, watched a kilonova bloom. The spectra told of heavy elements pouring into space, an R-process factory operating at cosmic scale. Models suggest that a single such event can produce Earth masses of gold. The origin of the metal in a ring on a finger and in the circuits of a spacecraft is not peace, but collision. Not stability, but a tidal tear between corpses of stars governed by Einstein's curved spacetime. With these observations, the gold world rumor loses its literalness and finds its power. The planet of gold becomes a thought experiment anchored in real data. Super-dense rocky worlds that reveal extreme differentiation, a metal asteroid that will tell how cores form, a kilonova that mints the heavy end of the periodic table. The deeper investigation says, if a single element ever dominated a world, what violence and what history would be required? The mystery sharpens because the extremes refuse to end where intuition expects. Measurements improve, and still, some exoplanets press toward physically startling densities. For a tense interval before Gaia corrections or better radial velocities arrive, a point on a plot might sit above the iron line, whispering of material compositions that are nearly elemental. Even when revision brings it back to plausibility, the approach itself is a challenge. Planets can become almost naked metal. The environment of those worlds is another shock. Ultra-short-period planets live so close to their stars that their day-sides simmer at thousands of degrees. Rock vaporizes. Magma oceans convect. If a world somehow contained enough gold to paint a fraction of its surface, would it last? Gold melts at 1,064 degrees Celsius and boils above 2,800. Many lava worlds exceed those thresholds. Radiation would sculpt exospheres laden with metal vapors, sodium, calcium, iron, detected in several hot worlds already. Gold's spectral lines lie mostly in the ultraviolet, cloaked by the star's glare. A glint from a golden mirror would be a fantasy of geometry and atmosphere that real photometry would likely see as heat, not reflection. And yet the galaxy's chemistry is not uniform. Dwarf galaxies like Reticulum 2 show signs of being enriched by a single violent R-process event. Some stars in the Milky Way's halo carry heavy element ratios far beyond the Sun's. If a protoplanetary disk formed around such a star, local chemistry could tilt toward the heavy end. Does that raise the ceiling? It does, but not enough to justify a pure element world. The R-process pours out a stew, not a single flavor. Gold is born with europium, platinum, lanthanides, actinides, an orchestra of heavy. To refine one into overwhelming purity without biology or industry would require processes nature does not perform at planetary scale. The deepening is not about debunking a headline. It is about seeing how close reality already runs to the edge. Giant impacts do strip mantles. Stellar radiation does carve down planets. Cores can be left exposed to space, the way TOI 849b may be the exposed heart of a once gaseous world. In that context, a gold planet is not a hoax, it is a limit case. It asks whether physics will allow a world to be dominated by a single heavy element. The answer is almost iron, perhaps. Gold, no. And that no has to be explained precisely with the tools of cosmology and chemistry. Several models now sketch a pathway to metal-dominated worlds, each anchored to observations. Inner disk condensation and drift. In the hottest parts of a protoplanetary disk, metallic iron condenses at higher temperatures than silicates. Pebble accretion funnels material inward. Over time, gradients and gas drag can segregate populations, leading to planetesimals with an outsized metal fraction. Worlds born here start heavy. Giant impact stripping. Kepler 107's inner pair tells the story. Two planets of similar size show wildly different densities. A plausible cause is a Mars-sized impactor striking at escape velocity, blasting away a mantle and leaving a Niren-rich remnant. Mercury itself may be a museum of such an event. The photoevaporation and core exposure. Planets huddled close to their stars are sandblasted by X-ray and extreme ultraviolet light. An originally larger rocky world can lose its lighter materials, trending toward a higher core fraction. For sub-Neptunes, this process can strip the envelope entirely, leaving behind a dense, naked core. These are not conjectures. They are now standard ingredients in interior models and population studies. They explain the super-Mercury population without invoking exotic chemistry. They push the mass radius points toward the iron line. They open space for metal worlds. To push further toward gold requires stepping into speculative light. Three ideas stand at the fringe. Our process enrichment at birth. Suppose a molecular cloud collapses in the wake of a recent neutron star merger, and the protoplanetary disk captures an unusually high heavy element budget. The disk's overall metallicity would rise, and gold's absolute abundance would climb. But even under heroic enrichment, gold would remain a trace among heavy elements. The stew does not separate itself. Chemical sorting at planetary scales. Over geological time, siderophile elements migrate toward cores. Gold, a textbook siderophile, would partition into metal alloys deep below, mostly with iron and nickel. This actually works against surface gold. The planet becomes less golden to the eye the more geologically mature it is. Only a core, a place unseen, would hoard it. Exotic matter or dark sector objects. Rare theoretical frameworks propose macroscopic dark matter nuggets or strange quark matter that could masquerade as ultra-dense, chemically peculiar objects. If such a body captured a sheath of normal matter, could it present densities that confuse interpretation? Perhaps. But this belongs to the realm of hypotheses seeking evidence, not explanations guided by it. NASA has found no object that demands such a solution. There is one more speculative path, smaller but real. If a lava world's dayside vaporizes silicates and metals, its nightside might allow condensation of particular species. Industrial civilization could, in principle, mine the vapors and plate a surface in gold. That is engineering, not nature. It shifts the question from astronomy to anthropology. The models that survive are humbler and stronger. They say, planets can be carved down to metal by heat and impact. Iron can dominate. From neutron star mergers, gold falls like frozen rain across a galaxy, but it does not pool into planets. Einstein's curvature tells where those mergers happen. Hawking's work on extreme gravity's thermodynamics sketches why collapsed matter is the end of that road. Between those poles, the hot young disks and the cold, dead stars, chemistry is a combination lock that refuses a single number solution. The Golden Planet is a story told by longing. It takes an element that civilization chose as a measure of value and imagines a world made entirely of it. But the cosmos is not an economy, it is a history. In that history, gold is a footnote with a violent parentage. It is crafted in collisions so intense that time itself stumbles, where space-time waves move across a universe Einstein described and detectors built by human hands here. The element that crowns kings is born in the ruin of suns, so the true revelation is quieter than a headline. It is that when scientists speak of a metal-rich world, they are not promising wealth, they are reading scars. A dense exoplanet is a memory of heat and subtraction, of mantles torn away and cores revealed. A metal asteroid is a chapter ripped from a planet's interior and left to drift. A kilonova is a birth announced in ash and light. What does it mean for a species that named its ages after metals to discover that in the largest age, the cosmic one, gold is neither meaning nor measure? It means that value is a local verb, not a universal noun. It means that the most precious thing about a golden planet would not be its metal at all, but the fact that it would force minds to learn, to refine, to ask better questions. There is no planet of pure gold. There are, instead, better things. Worlds that press against physical limits, instruments that can weigh them through the flicker of distant stars, and a species that can turn rumor into reason. In the darkness, a plot line is richer than any metal. Matter condenses, worlds appear, collisions sculpt, and from those scars, consciousness rises to read the universe and to discover that even a myth, told carefully, can be a door. Viewers who value slow mysteries and evidence over rumor can support more journeys like this by liking the episode, sharing thoughts in the comments, and subscribing for future explorations of space, time, and the edge cases of physics.